Good afternoon, everyone. Today we have Riya with us. Hello, Riya.
Hello, good afternoon, everyone.
So Riya is a M.Tech student at IIT Pune. She's in second year and she's doing her master's thesis on quantum computing. So I thought that it would be a great idea for her and for you also to interact and talk about quantum computing. So I requested Riya to spend her 1 hour with us today and enlighten us about quantum computing. So Riya, thank you so much for accepting to talk to us, and we look forward to uh, your thoughts on quantum computing. So over to you. Thank you, Riya.
My pleasure is all mine. Before moving on to quantum computing and such, um, ma'am has given a very brief introduction about me, so you don't need more. But yes, I'm working on quantum computing, but I'm using it for quantum cryptography. There are multiple ways in which we can use a quantum computing methodology. We'll discuss it at the end, so you might also get enlightened what are there. So yeah, let's begin with our presentation. Before moving on to quantum computing, let's look how the evolution of computing took place from the ancient times. So it all started with abacus, the ancient Chinese instrument they used to count and compute numbers, do multiplication, etc. Then came in punch cards. In earlier times, they used to do computing with using those punch cards, where the holes are inside the punch cards. I will not go more in detail, but those were the areas where which the connection happens with the computer and current parts of it. And this is how computing was done through punch cards back then. Then came vacuum tubes. These were also called the first generation of our digital computers. So they were big rooms of uh, centers filled with these um, racks of vacuum tubes on which computing was performed. So where basically the cathode rays were used as in control of whether it's 0 or 1. Then came in the transistors, and this revolutionized all of our computing architecture and sort of. And I sure Yashoda ma'am must have shown the transistor switch working as a switch 0 and 1. So you will be pretty aware of that. And then we came to integrated circuits. We made those transistors smaller and smaller so that it can be easily compacted and filled inside the integrated circuit. And then came very large scale integration. So we made it way more smaller. And we are currently in this stage, and we are, increasing the number of transistor that we can fill in a small given area. So this is the history of all the uh, transistor size that we made, and the number of the length of the transistors that we scaled down to. So as you can see, we started with 100 picometer to 3 nanometer in 2022. But as the gradual increases there, you can also see that there is a reduction in the reduction in the size of the ability to reduce the size is also reducing. So in say 1990s and 1993, in 3 years we scaled 250 nanometers, but in this 4 years we could only scale it down to just 1 nanometer. And also the added R&D cost is also increasing. So there is a limit till which we can actually uh, keep on decreasing the size of our transistor to fit into a given area. And we are slowly reaching the roadblock for that. And so, where do we get the processing power for our AI and big data sort of processing if our hardware cannot provide it? So, there are multiple other technologies that scientists came up with, and one of which is a quantum computer. So, he is a new kid in town. So, before, like, what is a quantum computer? Like, is it similar to our own desktop computer that we know, or is it sort of different? So we'll take in a compare, we'll study it in a locus to our current computer so that we can compare it on a case by case basis. So moving on to introduction. So in the left, you can see our classical chip. You all must have seen this, right? And what is this? This on the right is a quantum chip. Quite similar, right? But they are different. Of course, scale-wise, yes, they are similar. This is also very tiny chip, similar to the scale of the classical chip. And on this classical chip, there are millions and trillions of transistors. But on this quantum chip, there are qubits. So these little squares, you can see they are qubits. Uh, just like we have bits in our classical computing, we have quantum bits or qubits in quantum computer. And this is just one type of quantum computer chip. And these qubits are made up of superconducting rings. And you can think of these qubits as transistor on your classical chip. So qubits are equal to your transistors. Now, this chip, classical chip that we saw, goes here somewhere here in your desktop or a laptop, and then other wires connecting it through the different parts of the unit of our laptop. But in a quantum computer, the chip sits here. I hope the color is visible. And these are the microwave tubes through which the chip is being connected to its processing unit somewhere here above. And these whole chamber is then sealed, as in refrigerated, to close to 0 Kelvin. And this is where the superconductivity of the rings happen, and we can do quantum computations in that. And this type of quantum computer is majorly used by Google, IBM, and NASA. Over to the bits and qubits. Now, we saw a quantum computer, but we don't know how it works. For that, we need to look at its fundamental building block, which is almost analog to a bit that we saw earlier. So, in classical computing, a bit is either a zero, binary, right? 0 or 1. But in quantum computing, qubit can be both 0 and 1 at the same time. So it can be with a different proportion, but so all these qubits have both 0 and 1 at the same time, but with varying proportions. And this is because of quantum property of superposition of multiple states that can happen in a quantum system, which is also a qubit. So let's compare like how a qubit can be compared to a bit. So one qubit is 2 to the power 1 bits. That is 2 bits. And 2 qubit could be 2 to the power 2, that is 4 bits. And 3 qubit could be 2 to the power 3, that is 8 bits. Now, we saw these root 3 by 2, 1 by 2 values previously, right? Here. So what were these? So a qubit state can be written as alpha times 0 state plus beta times 1 state. Now, what are these alpha and beta? Alpha and beta are the complex probability amplitude, which can be simply understood as a probability of the qubit to be in state 0 or 1. But there is a bit of caveat that it's a complex probability. It's not a whole rational number that we deal with in a classical probability. It's more of a complex number. But for now, just consider it to be rational number for our easy understanding. So a qubit state can be denoted as alpha times 0 plus beta times 1. Now, notice the symbol, this symbol, this one that we have used here. They are Dirac's notation. It's called bracket notation. So what it means is that any quantum system in quantum mechanics requires to use Dirac's bracket notation, but for our understanding, they can be easily understood as a row vector. This is called, and it's a column vector. Oh, I messed up. It's a column vector and it's a row vector. So state 0 qubit can also be written as a vector of 0, 1, and state 1 qubit can also be written as a vector of 0, 1. As you can see, it's a column vector. So they are Dirac's bracket notation, and this is pronounced ket 0 and ket 1. So ket A will be a column vector A, B, and bra B, denoted by the symbol, will be the row vector A star, B star. And if we try to write our state 0 and 1 in terms of the psi and the alpha and beta values, how it will be is that psi is equals to alpha times 0 plus beta times 1. So we can replace the 0 and 1's value here. So alpha times 1, 0 plus beta times 0, 1. And simple our matrix addition, we can perform in multiplication, scalar multiplication, and we'll get alpha and beta as in vector. So understanding quantum computing through vectors and matrices, it's very easy. And we use it for making it more mathematically simplistic, because the state of a qubit can be easily understood in the vector space. Okay. But the actual qubit lies in Hilbert space. Although we try to represent it in a vector space, the qubit actually lies in a Hilbert space because it is a quantum object. Now, what is Hilbert space? We don't know that, so we'll understand it through vector space. Vector space, as we know, is a three-dimensional space wherein we have three axes: x, y, and z. Unlike vector space, Hilbert space is an n-dimensional space. So there are n dimensions denoted by psi 1, psi 2, psi 3, psi 4, and so on. Here we only have 3 dimensions. In Hilbert space, we have n dimensions. Since we have 3 dimensions in vector space, we use 3 bases. Basis is just a measure for the vector space. So we always use, when we pinpoint a space in a vector space, we always denote it with x, y, z coordinate, right? So these are 3 bases. So we always measure respect to those coordinates. So we have 3 bases: x cap, y cap, z cap. But in Hilbert space, since we have n dimensions, we also have n bases. And this will be psi 1, psi 2, and so on. And we also know that these bases are also unit vectors. So x, y, z are unit vectors. Similarly, in Hilbert space, they are units, but they are unit functions, not vectors. So Hilbert space is n-dimensional space with basis as a function. So unit functions, which are psi 1 to psi n. And since vector units, they are unit vectors, so their magnitude will be always unity. Similarly, these are unit functions, so their magnitude will also be unity. Now, Hilbert space is very difficult to visualize and imagine, and we cannot always visualize qubits in Hilbert space. So to make our thing easy, we have another graphical representation in vector space called blot sphere. So as you can see on the left, this image is of block sphere, and this equation specifies where the qubit lies in the block sphere. So as we saw earlier, psi is equals to alpha times 0 plus beta times 1. So comparing these both equation, we can see that alpha is cos theta by 2 and beta is equals to e to the power I phi sine theta by 2. And you can, notice this theta and phi on the block sphere. So this is theta and this is phi, right? So for the state 0, which lies in the topmost position of the qubit, you can see that theta is 0 and psi is also 0. For the state 1 of the qubit, which lies the bottom most part of the block sphere, you can see that theta is 180 degrees and phi is 0. So when we put those values into alpha and beta, let's see whether we can get the exact 0 and 1 also or not. So let's put our values for state 0. So alpha is equal state 0, where we have theta is equals to 0, phi is equals to 1. So alpha is equals to cos 0 by 2, which will be 1. And beta will be ei phi sine 0 by 2. This is also 0. So this tends to 0 and we have a 0. So our state 0 can be denoted as 1 times state 0 plus 0 times state 1 is state 0. So LHS is equal to RHS. Similarly, we can do for our state 1 also. For state 1, it is theta is equals to 180 degrees and phi is equals to 0. For alpha, it will be cos 180 by 2, which will be 0. And for beta, it will be e to the power I times 0 sine 180 by 2. So this tends to 1 and this also tends to 1. We are not tends to, it's equal to 1. So we get beta 1. So we write state 1 in form of alpha beta as 0 times state 0 plus 1 times state 1. So we get state 1. So again, RHS is equal to LHS. So now it's easy to visualize a qubit in blocks here, and we can easily denote it anywhere in the block sphere. Now, although we saw how to represent it in vector space and block sphere as well, but why do we use this psi and quantum notation and direct bracket notation, etc.? Why can't we just use matrices, vectors, and not make it all complicated? So there is a reason behind it, because qubit is a quantum mechanical system in itself. You must have taken classes of mechanics in your 11th and 12th. So if a mass is m and if it has got velocity v, its momentum would be m times v, right? And this will be same, the momentum of the mass will be constant throughout the time. So if I say let me pinpoint me the position of that object in time t1, you can easily say that at t times 0, it was mass was at point, say x is equals to 0. At t is equals to t1, you can easily pinpoint the position of the mass that it will be in, because you know the velocity, and consider an ideal situation where friction is not there. So you can easily find the distance x, right? Or say, and the position x1 in space. But in quantum mechanics, it's not so easy. So imagine that this mass, we squish it so small that we come to a quantum level. So it's very tiny. So it's a quantum mass now. And now it has got some momentum p. Um, and we need to identify what will be the position of that quantum mass in time t1. And when we find the answers, it's very different than what we know about our classical mechanics. The answer is in probability. So there will not be a single place where the quantum mass is present, but multiple places where a quantum mass can be present. And the answers will come in probability. So for quantum mass to be in this place will be 70% of times, and this will be chances are 50%, and here also 15, and maybe any n number of possibility. So this equation that you are seeing in the left is this momentum equation of an electron. It's very complicated, so don't go into it. But basically, it just states that we always get a probability of finding an electron in a position X, and not exactly a position with 100% certainty. So qubit also follows this kind of equations of these kind of quantum mechanical properties. You also must have seen this diagram in your chemistry classes in your 11th 12th as well, with your Schrodinger equations and uncertainty principles. Okay. Now the another fundamental that we need to talk about is that, I hope it's visible. When we try to plot the intensity graph of these inference pattern with the displacement x, so here intensity and the displacement x is the displacement from the center of the screen, we'll observe a pattern like so. At the middle, that is x is equals to 0, it's the highest intensity. And then the intensity keeps on reducing and at some point of time, it's reaches 0. So the places where there is no light or not there, these empty places, are the places where the wave was destructively interfered with each other. And the places where the light is present is where the waves constructively interfere with each other. So if they constructively interfere, they increase the intensity. And if they destructively interfere, that is of different or opposite polarity, they cancel each other out. So similar to noise cancellation headphones that we know of. So this is also a quantum mechanical property of particle wave duality that qubit follows. And also an electron has a property called spin. So electron can be either spin up or spin down. Similarly, the qubit can be in state 1 and state 0. But electron can also be in both the spins up and down until you tend to measure it. So it's kind of superposition of spin up and down. Similarly, a qubit has state 1 and 0. So an electron can be also made as a qubit. Okay. Another property that is quite different and not found in a classical computation is quantum entanglement. So, quantum entanglement, to understand quantum entanglement, consider two people, Alice and Bob. They both have an electron, half a pair of electron, or rather, they both have a qubit, for example. Even if they go far further apart, say two different ends of the Milky Way galaxies, or maybe two different ends of the universe, there is a strange connection or a property that keeps these qubits entangled. That if and when we try to interfere with a half the pair of the entangled pair, the result is also shown on the other one as well. So if I try to say measure this qubit, we'll talk about measurement later. If I try to interfere with this qubit, say change its state. So if its state will be 0 and I change it to 1, similarly this qubit magically will also go into that contrary change that we did on the first qubit. And this quantum entanglement was so weird that even Einstein discarded this theory as spooky action at a distance. So we know this phenomenon happens, but we actually don't know why it happens. So we have observed it, but we don't have a mathematical reason for it. But that is happening in nature. So as in we can use it in our computation as well. Okay. Next is how we saw the qubits and etc. But how do we modify it? With bits, we have gates through which we can, do our computation and etc. So we know our NOT gate A and let me write its truth table 0, 1. So when we apply 0 to NOT gate, it will convert it to 1. And when we apply 1, it will be 0. So what it happens is bit flip, right? NOT gate does bit flip. Similarly, we have quantum gates in quantum computation. These gates are X gate or poly X. Let me write it down. Poly X or X gate, poly Y, poly Z, and the last one is Hadamard or H gate. So what poly X or X gate does, it bit flips or causes bit flips of the qubit, or rather state flips. Poly Y does a combination of a bit flip and phase flip. Poly Z or Z gate does phase flip. And Hadamard creates superposition. We saw earlier that state of a qubit will be both 0 and 1 at the same time. So this is all what Hadamard can do. So let me actually show those gates on a real composer, quantum composer. So we have a qubit here, and this is a Q-sphere on which the qubit can be seen. So currently it's in 0 states. So it's a default state like any bit also, where 0 is our default bit, default state of a bit. So as we saw here, X gate, let's apply an X gate. So X gate or NOT gate is denoted by this plus sign here. Before that, the qubit is in state 0, so it's a gray. And when I apply a NOT gate, you see that the qubit went into state 1. And yeah, it can be also shown in the vector here, graph here. And the color of the qubit also changed to blue, that is state 1. Now let's check with Hadamard. Yeah, Hadamard is this edge gate. You can see that the qubit is in 50-50 superposition of state 0 and 1. And even on the amplitude graph, you can see that it's around 50% of times 0 and 50% of times 1. Let me show a Z gate. Z gate does not change the state of the bit. It keeps as it is. Now let's see like how it's been represented in metrics as well, how the gates are represented in metrics. So we saw earlier that 0 can be represented as 1 0 and 1 can be represented as 0 1. The matrix notation for our qubit states. So when we apply X gate, it's simple matrix multiplication. X to the qubit 0. What happens is, this is the matrix notation for the X gate. We write 0 1 1 0 times state 0 1 0, and we do matrix multiplication 1 times like matrix multiplication, and then we get 0 1, and this is the state 1. So as you can see, it caused bit flip. Now what happened if you apply X gate to state 1? So X matrix we write, then the one state matrix. So we have, after matrix multiplication, we have state 0. So as you can see, X gate caused the bit flip. Let us apply Y gate to both state 1 and 0. So Y to state 0, matrix of Y. Notice that we are using I because these are complex, and we also have complex probabilities as a state in qubits as well. So applying, to state 0, we do matrix multiplication, and we obtain 0i. We'll take I common. It will be 0 1, and this is same as state 1, so it will be I times 1. So it's both a phase flip from real axis to imaginary axis, and also the bit got flipped from 0 to 1. Let's apply Y gate to state 1. So 0 minus I 0. 0, 1, the state for 1, do matrix multiplication, we get minus I times 0. We'll take minus I common. We have 1, 0. And so we have minus I times 0, right? So again, face flip and bit flip. So we came from real to imaginary axis and also changed the bit from 0 to 1. For Z gate, applying it to state 0, 1, 0, 0, minus 1 times the state of 0, 1, 0, and what we get is 1, 0. So as we saw earlier, the state of the qubit did not change. We again get the 0 qubit back. So it does not affect the state of a qubit 0. Now what happens when we apply it to 1? So it will be 1, 0, 0, minus 1 times 1, 0, 1, and we get 0, minus 1. We can take minus 1 common, 0, 1. So our one state, we get a negative sign. So the face got flipped. We came from the positive direction to the negative direction, if that makes sense. Next, we need to see Hadamard gate because this is the interesting of all. If you apply Hadamard gate to state 0, let me write state 0 again, 1, 0, and state 1 will be 0, 1. So we saw in the quantum composer that when Hadamard was applied, we get a 50-50 superposition of both 0 and 1. So let's see if we are getting this here also. So matrix of Hadamard, 1, 1, 1, minus 1. And for qubit 0, 0. And we obtain 1 times 1. Now, if we're trying to separate it, as we saw earlier, it will be 1 times 0 plus under root 2, 0 times 1, right? So it's same as state 0 and 1. So it can be written as under root 2 state 0 plus under root 2 state 1. So it's an equal superposition of both 0 and 1. What happens if we apply Hadamard gate to state 1? Let us see. Writing the matrix of Hadamard and doing the matrix multiplication. Separating 1 and minus 1 as so. Minus under root 2, 0, 1. You can see that we have equal superposition of state 0 and 1, but the relevant phase or the polarity of state 0 and 1 is different because 0 and 1 there is equal superposition with the negative polarity compared to each other, and here they are in positive superposition. Okay. Next, we understand how quantum gates can be used to modify the qubit states, but how do we know actually that it's been modified? And for that, we measure the qubit. So in classical computing, we don't measure bits, right? It's just we do computation and we get the output. But in qubit, unless you do not perform measurement, you might not know what is inside the qubit. But there's a caveat. In bits, if we try to read a bit out, even if it's stored in any corner of the computer or server or anywhere on the internet, it stays there after reading, right? It does not destroys itself. But when you try to read through a qubit, the act of that reading or the measurement collapses the qubit and makes it to a classical state, and we only have that state, and we have lost all the information that was previously present in the qubit. So measurement is very tricky because we only perform measurement when we actually want to know what is in the qubit uh, after everything. So there are basically three, not basically, but mainly three types of measurement that are predominantly used in quantum computing. They are X, Y, and Z measurement. So just like the axis of the Bloch sphere, X, Y, and Z, bases on those vectors of the Bloch sphere, we perform measurements. So this is the symbol for measurement. And when a qubit is being measured, it is then decomposed into a classical bit, and the quantum state gets collapsed. So if a qubit is in a superposition, when you try to measure it, superposition will be destroyed. Okay. So for X measurement, these are the bases: plus X and minus X. So X-axis on Bloch sphere, I will extend it a bit. So the point at which Bloch sphere and the X-axis intersect, these 2 points are the plus and minus bases of the X measurement. So a qubit state can either decompose into any of these measurements when we try to measure. So when we actually apply measurement, what happens is just the inner product. So if I measure the qubit state 0 with a plus measurement, what I will be doing is I will be just multiplying or causing it inner product. So state of 0, since it's a row vector here, so it will be 1 comma 0 times the plus, which is an equal superposition. So 1 1, and root 2, cannot forget that. Simply multiply it and we get an answer. It's under root 2. So when we multiply these two metrics, right? So it's just a normal inner product or multiplication in the matrices. And measurement is generally denoted by this inner product. And for X measurement, we have these two bases. And similarly for Y measurements, we have I and minus I. So if I extend the Y axis, these 2 points plus I and minus I. We measure our qubits in these 2 points. And there is Z measurement, is the easiest of all. And it's just measuring in state 0 and 1 directly because it lies on the Z axis of the Bloch sphere. Okay. Now coming to no cloning theorem. So when we try to read a bit and try to make its multiple copy, we can do it a number of times. Say you can make multiple copies of a document, multiple copy of a txt file, etc., etc. But if it's a quantum bit, you cannot clone it. You cannot make multiple copies of it until and unless you know how it was created. So what happens is, in classical cloning or the normal copy paste that we do, we go to the location, say 239, for example, somewhere in the memory there is 27, return it. We go to the location, read the value, and then go to somewhere 1089, and then read this value and write this, create its copy there. It's very simple. But in quantum computing, when we try to go to that place, for example, in quantum memory, and read that qubit, say it's some state psi, we measure it. Alas, the qubit got collapsed, and we just got some answer, state 0, and we have lost all the information what was previously present in the state psi. So until unless we don't know how the state psi was created, the gates that applied, and even the sequence of gates, we cannot create this qubit back. So we cannot copy paste a qubit. Okay. Yeah, that suffices with the presentation. But I don't know if I have time. Yeah, it's 1 o'clock. I have some programming file that I like to show it very real quick. So, simulating a qubit on.
Finish.
Sorry. So, I'm simulating the qubit using quantum circuit. I'll share this file also with you, so it won't be a problem. You can check it by yourself. We use a quantum circuit function to create a qubit named QC. Since it's a single qubit, we write 1. And just a minute, it's initializing. So I'm using Qiskit for Qiskit is a library that enables us to simulate a quantum computing in simulating quantum computing programming on your desktop as well. So through which we can simulate quantum computations on a classical desktop. And so I'm simulating a single qubit circuit here in QC. And we'll draw that QC circuit. As you can see, it's an empty because we haven't done any computation onto the qubit, and it's in default state 0. Now we apply an X gate and then draw the circuit QC. So as you can see, the X gate is applied on the qubit state 0. We can also apply the H gate. So as you can see, the H gate is added after the X gate. So it gets added sequentially, and sequence is very important in quantum computing. If you invert the sequence, the output can change. We can also apply Z gate. We'll quickly see measurement. But for measurement, we need to add a classical bit. So I've written quantum circuit 1, 1. what it creates is this double line that you can see below the X gate. Uh, Double line that you see below the X gate is the classical bit on which we read the measurements. And we measure it on the qubit, for which we use a measure function. And then we simulate our circuit on a quantum simulator. And we print our output, which is 1. That is, when we applied X gate on the default state of a qubit, we get state 1. And then we can also visualize it in the form of this histogram. Yeah. That is all quantum that I can give onto you. Thank you.
Thank you, Riya, so much. I am requesting students if they have any questions to ask.
Ma'am,
Yes.
uh, what if I want to study in this field? Where do
Yes.
we start?
Yeah, you can study, you can start anywhere. Internet is on internet, you have got all the resources. But with Qiskit library, they have got their own lectures that you can find. I can also share the resources with you, and yeah, you can study it very easily. There are a couple of textbooks you can start with, and even some courses online as well.
Ma'am, in my case, I'm studying quantum physics for last 2 years, excluding the mathematical part.
Mhm.
तो मतलब कहाँ से शुरू करूँ आगे?
So, since you are already so good with your quantum physics, you can easily start to simulate those quantum physics onto programming it on a computer. So, start by learning Qiskit library. Just as for machine learning, you have different libraries. Similarly, you have Qiskit for quantum programming. Try to learn. There is also other called Circ, but which is developed by Google. So you can learn those and start simulating.
And I have another question. As we know, when we have to entangle particles, and if we try to change the state of anyone, the entanglement मतलब broke. So if we can't change the state, how we can use in computing? If we
Uh,
can't
I
change
didn't.
state.
I didn't got your question. Do you mean to say that uh, when
If we
we
can't change the state of two entangled particles, how we
no,
can
no,
use?
no, no. We can change the state of the entangled particles. It's just that when we try to modify one, the other also gets modified magically.
मैम ये क्वांटम इंटेंगल का प्रिंसिपल क्वांटम टेलीपोर्टेशन में भी यूज होता है ना?
In the theory, yes. We can use quantum entanglement for teleportation as well, because you can send in your data easily. Because when you modify a state of a qubit here, the other half also gets modified. So teleportation के लिए भी यूज हो सकता है, क्योंकि हम अगर यहाँ क्रिएट करके वो वही दूसरी कॉपी वहाँ क्रिएट कर दे और ये कॉपी डिस्ट्रॉय कर दे, then you can easily send matter through the entanglement. But in theory, abhi tak physically we are not able to do so, apart from a single photon or levels of quantums, not a big object like a human or any big thing. But in theory, yes, it is possible.
मैम, ये जो भी क्वांटम फिजिक्स के रूल्स होते हैं वो मतलब बहुत ज़्यादा कम स्केल पे वो होते हैं ना, तो हम लोग इतने कम स्केल पे हम लोग चिप्स ये सब फैब्रिक कैसे करेंगे?
ये चिप्स कम स्केल की है, smaller, but they work on electrons, right? Electrons are quantum objects, or they are being done in closer to 0 Kelvin in the computer that I showed you. So wo state pe they can create certain conditions wherein we can observe the quantum mechanical properties and use it for our needs like computation.
मैम आजकल के सुपर कंडक्टर को तो 0 केल्विन की जरूरत नहीं होती, यानी वो 170 केल्विन तक भी चला जाता तो।
but but for this computations we need closer because we need to create those conditions for computation. But there are certain computers that don't require 0 Kelvin, that can work on room temperatures. They are called diamond vacancies based quantum computers. So diamond का जो crystal lattice होता है उसमें बहुत सारे empty spaces और vertices होती है. Therein they inject nitrogen component and with lasers and etc things, and through that an electron they do computations as well. So it's a different yeah, but possible as room temperature as well.
मैम और एक क्वेश्चन था कि क्वांटम मैकेनिक्स क्रिप्टोग्राफी में कैसे यूज हो रहा है?
Okay, so I'm working in quantum cryptography for my thesis as well. So वो cryptography में ऐसे use होता है कि whenever a fully tolerant quantum computer will be available, uh, your cryptographic system will be totally unreliable, because you must be aware of RSA and all the key exchanges protocol that we use today. So those can be easily cracked by a quantum computer, maybe in minutes. So we cannot use our classical functions or classical systems to protect our cryptographic system from the quantum computer, if at all will have in future. So we use a quantum computer or quantum phenomenon or quantum uh, quantum principles itself to create those key sharing environments or key distribution, and one of which is to entanglement as well. So we share our keys to entanglement by changing the state. So yeah, we use it in that way.
Okay, any other question? Riya, there were two questions on the chat. So one of them was, what is the purpose of quantum computer?
Okay. So for that, let me say, when there were no computers, somebody might have thought, what is the use of computer? So it's just that computations are always increasing. It's not that we don't have a use case now that we will not be requiring in future, right? When the computers were discovered, people might be also they were only meant for the military and etc. General public did not have computers. So use cases will be developed as and when the computation speeds requirements will be increasing, the data that we have today will be increasing, the search space for our of our trends of all our data that we store in cloud or anywhere increase, and then will be requiring a quantum computer. And there are scientists working in quantum computing to solve problems like climate change also. So these problems of climate change and etc., they require tons and tons of variables to consider at a time, and a classical computer cannot always consider. Even the biggest supercomputer that is currently in Tokyo, Japan, is not so advanced that it can, solve for all those variables there. So we need higher computation powers. Also considering example of drug discovery, so wherein the protein folds, they simulate how the molecule interact in terms of proteins and etc. So there is so many possibilities to molecules and proteins interact in chemistry and etc. And they need to do trial and error, n number of times. But what if they could simulate all those possibilities on a computer? So quantum computer could change that simultaneously. They can simulate all the possible options and get to our drugs, even vaccines, easily.
Mhm.
That's great to know. One more question was what info we get before a qubit collapses?
Yeah, so we get an info that is a classical analog of its states. So if a qubit is in multiple states, say 50-50 superposition of both 0 and 1, when we try to measure it, we'll get either 0 or 1, any of the two. So we can say that qubit was in state 1 because we measured it. But since it was in superposition, we lost that superposition. But we didn't know that it was there because we didn't get in the output.
Okay. Okay. And one more question. Do you think there is a potential use of quantum computing in blockchain?
Uh, yes, there can be, because blockchain is more maintained by the number of computers that are connected to it. What if a quantum computer enters into that ecosystem? It might change capture the load for that, s- replace the load, even half of the ecosystem, get hold of the half of the ecosystem, because it's way more powerful than all the other computers that are present in the blockchain, and they might cause a problem as well.
Yeah.
मैम और एक था कि गूगल ने 9 साल पहले ही अपना क्वांटम कंप्यूटर इंट्रोड्यूस कर दिया था, बट अब भी वो प्रोडक्शन में नहीं है, और कोई उस वहां पे उन्होंने वीडियो भी नहीं किया। 9 साल पहले किया था बट अभी तो कोई रिपोर्ट नहीं की। क्या उसमें कोई इनोवेशन नहीं हो रहा कि अपन कहीं स्टक हो गए, ऐसा कुछ?
Google currently is just created a quantum AI center for it. So Google नए use cases try कर रहा है using those quantum computers, or that the quantum supremacy that it claimed few years back. So उसके लिए use cases ढूंढ रहा है. So Google is also trying to spin off a new company out of it, specifically um, for those use cases and applications of quantum computer. So in future, you will be seeing more companies that provide this, quantum computing as a service, and companies and other people can also leverage those quantum computers. You will not see actual quantum computer, in your house anytime soon, or even, you will be just seeing those used frequently for computation as a service, of course, because it's very difficult to maintain one.
मैम आई वांट टू ऐड समथिंग कि 9 साल नहीं हुए, 2019 में गूगल का जो सिकामोर नाम का जो क्वांटम कंप्यूटर है, उसने अपना पहला जो ट्राई किया था, उसमें उसने जो काम 200 सेकंड में किया था, वो हमारा जो जापान वाला सुपर कंप्यूटर है, वो उसके लिए 10,000 ईयर लेता था, तो वो सक्सेसफुल था वो।
Yes, thank you. Yeah, that is what I was talking about as well.
Okay. Any other question, guys?
मैम मतलब आप आगे क्या करने की सोच रहे हैं, मतलब आप आगे आगे के स्टेप्स क्या हैं, मतलब इस फील्ड में वो थोड़ा बता देंगे तो सही रहेगा।
इस फील्ड में बहुत सारे स्टेप्स है. क्वांटम कंप्यूटिंग इज मोर ऑफ अ method, it can be used for different things, right? It can be used for say quantum AI के लिए use हो सकता है. We can increase the capabilities of an AI. It can be used for quantum machine learning, wherein we can simulate our models on quantum computer, say classification or regression, etc. We can use it for optimization because we can study all the possible solutions simultaneously in superposition and we can identify the correct one. It can be used in chemistry for drug discovery. So, you know, use cases will be the actual driver for the technology. And yeah, the use case that I'm using, quantum cryptography. So that will be very relevant. Yeah. So more use cases will be coming anytime soon, and it will be coming from students like you that will be, be future experimenting in quantum computing as well.
मैम अभी जो हमारा मतलब ज़्यादातर चीज़ों में हम लोग जो इंक्रिप्शन यूज़ करते हैं वो क्वांटम कंप्यूटिंग से आसानी से हम लोग तोड़ सकते हैं. तो मतलब अगर कंप्यूटर ये सब सक्सेसफुल हो गया तो वर्ल्ड सिक्योरिटी जेनवरी के लिए बिल्कुल.
हाँ, तभी big companies and actual governments are very so much involved in quantum computing is to start working on measures to secure our cryptographic system. So we have already begun with it, and recently NIST, if you must be aware, has also list out the protocols that are quantum safe and that need to be checked more, of course. And it's said by 2023 we might be having a winner. And so yeah, industry currently needs to start upgrading their infrastructure, and the quantum cryptography and post quantum cryptography research is going on. So hopefully till we have a quantum computer, we'll already done securing our system because people are working it right now.
मैम इंडिया में किसी के पास है क्या ये टेक्नोलॉजी? क्योंकि अभी IBM और गूगल जैसे इस कंपनी के पास है, कोई इंडियन कंपनी जो उसके ऊपर वर्क कर रही है?
India mein, we don't have a quantum computer, but you can always access one through IBM or Google. Google not, but IBM's quantum experience. The quantum composer that I showed you, you can also access IBM's quantum computer through cloud. So yes, you can access it, but a physical presence of quantum computer in India is not there. Hopefully, will get one. Yeah, Indian government should surely get one.
All right. Any other question, guys? Vishal, Deep, anyone else wants to ask any question? All right. Riya, students are also asking if they can get access to your presentation and the code file.
Yes, I'll share those easily. Just
Okay. So probably you can email to me. I'll share on the classroom.
yeah, best. I'll share the link and yeah.
Okay. All right. Riya, thank you so much for talking about this topic with us today. Got to know so much. Quantum computing as a word sort of demystified because of your talk today. Now we know a little bit more about quantum computing thanks to your very patiently delivered talk and very passionately delivered talk. So that speaks a lot about your inherent interest towards the field. And I hope you keep on doing the good work that you are doing and keep sharing the knowledge also with all of us and with many people around you. Thank you so much for your time and patience, Riya. It's really appreciated. Thank you so much.
It was all pleasure for me. Thank you very much, ma'am.
Okay. Thank you.